Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everyone. My name is Devi Parikh, and I'll be talking to you about some of my work on leveraging humans to hopefully make our machines smarter. So I'm interested in image understanding. So I'm interested in being able to take an image like this and sort of find all the objects, find all the people, figure out how these people are interacting with each other, how the objects are interacting with each other, what sort of the global activity that's going on, where this picture was taken, what's the scene, is it indoors, is it outdoors, and so on. So trying to answer several semantic questions about these images that we would expect humans to be able to answer, but we want to try and build computer vision algorithms that can do that. Right? But if you look at any one of these tasks, and if you look at sort of the state of affairs today, this is what you see. It doesn't matter what the metric is on the y-axis, doesn't matter what the actual task is, but we find that people are significantly better at solving these tasks than machines are today. Right? And we are all obviously trying to bridge this gap, but if you think about how it is that humans interact with machines today, it might not be super surprising why this gap exists. Right? So for example, let's say you want to teach a machine what giraffes look like. Right? What are we going to do? We're going to go online, we're going to download a bunch of images, and we'll find an image, we'll find an example of a giraffe and tell the machine, this is a giraffe. Right? And then we'll go look for another example, and we'll tell the machine, this is not a giraffe. Right? Here's another example, this is not a giraffe. This is a giraffe. This is not a giraffe. This is a giraffe. This is not a giraffe, and on and on and on. Right? But if you think about it, we know so much more about giraffes beyond just being able to look at images and say whether something is a giraffe or not. Right? For example, if you take zebras, instead of just saying that this is a zebra, I know that zebras are supposed to have 4 legs and a tail, and they look like a horse, except they're striped, and so much more. But none of this is being conveyed to machines. All we would do is take this example and say this is a zebra. We might say this is not a giraffe, and that's about it. Right? And now let's look at the flip side. Right? I talked about how machines are interacting with humans, but if you look at the other direction of how machines are behaving, right? What do machines today do? They take an image like this, and with extremely high confidence, they tell us that this is an airplane cabin. Right? They take an image like this, and again, with extremely high confidence, they tell us this is an amusement park. This is an aquarium. This is a badminton court. This is a bedroom. And I've only gotten up to B, right? I can go all the way up through Z and give you examples of seemingly ridiculous response. And these are outputs of a real computer vision system from a few years ago. It was state of the art a few years ago. And these are high confidence responses for these images, right? And it doesn't make any sense. We don't know why it thinks this image is a bedroom. It's not giving us any warnings that it might be confused. It just spits an answer out, and that's all we have. Right? And you might say that, well, this was from 4 years ago. We now have deep learning. Deep learning has solved everything. Well, not really. Here's the same image. And if you look at the responses that you get from, this is back in April, so a few months ago. And there's many generic responses that are fine, but the first time it actually spits out a basic level category. It calls this a kitchen, calls this a salon. And it also, again, there are no warnings. These are high confidence responses. There's no explanation as to why it believes what it believes. Right? So what we find ourselves in is a situation that looks something like this. Right? Both sides are frustrated. Humans think machines don't know what they're doing. They can't give us anything useful. Machines think, well, you're not telling me what you want from me. And we are stuck in the situation where there is just a gap between what humans want and what machines can do. Right? So what I'm claiming is if we have a better mode of communication between humans and machines, some of these issues might be alleviated. All right, so what I'm going to do for the first part of my talk is talk about how we've tried to use visual attributes as a mode of communication between humans and machines. And so attributes are just visual properties, things like furry, natural, young, and so on. They're mid-level concepts, so they're higher than just the low-level features like texture or color histograms, but they're lower than the high-level concepts that you might care about. And the nice thing about attributes is they tend to be shareable across different categories. So multiple animals can be striped, multiple animals can be furry. What I find exciting about attributes is the fact that they're human understandable, so they have a semantic name associated with them, and they're visual, so there's hope for machines to be able to detect them. And that's what makes them a good sort of form of communication between humans and machines. So what I'm going to do is I'm going to give you a brief overview of the different things that we've done in this space of trying to use attributes as a mode of communication between humans and machines. And I'm going to organize them along two axes. So I'll give you an overview of each one, and then I'll delve a little bit more into one or two examples. So these two axes, the first one is the role of the human. In this communication, is the human a user of the vision system? Or is the human a supervisor who's trying to train a computer vision system to learn a certain concept? Right? So that's the first axis. And the second axis is who's the communicator? Is the human communicating with the machine, or is the machine communicating with the human? And as I give you a brief overview of these examples, you'll see a little bit better what I mean by these. All right, so let me start with the first one, where the human is the user and the communicator who's communicating to the machine. So that first application is image search. Right? Let's say there's a user trying to interact with the system. The user has, I just realized that this example is going to be interesting given that I'm at Microsoft. But anyway, so you have a user that has a mental model of an image that he or she is trying to look for. And the first thing that you can do is you can query for certain keywords. You might get a set of images back, and chances are whatever you're looking for is not in the top results. Right? So traditional relevance feedback will just let you click on an image and say this image is not relevant to what I was looking for, or this other image is relevant, and so on. But the issue is these methods don't let you specify why something is relevant or how the image needs to change to become more relevant to what you're looking for. Right? So what we proposed was the use of attributes where a user can click on an image and say that the person, in this case, the person that I was looking for, looks something like this but is fuller faced. Right? So with this mode of interaction, the user can specify exactly how a certain example needs to change to better match their mental model or better match whatever it is that they're looking for. And what we showed in our paper at CVPR in 2012 was that using attributes as feedback gives you significantly better search results. You can find the image that you were looking for at significantly fewer iterations than if you were to just give binary relevance feedback where you're not explaining why something is relevant or how something needs to change. So that's one example. The second example is if I flip the roles, where the human is still the user of the system, but the machine is the one communicating, right? And so what might the machine communicate? Well, it would be really useful if a machine can communicate to a user the scenarios in which it tends to fail, right? So if the machine can communicate a semantic characterization of its failure modes, that would be very useful to a user. For example, a face recognition system might say that if the image is blurry or if the face is not frontal, then I'm probably not going to be able to recognize the person, right? So this doesn't make the system any more accurate, right? I'm not claiming that we would have a better facial recognition system as a process of this. But what this gives you is several things. One is, as a user, you know when to trust the system and when not to trust it, or when to use the system and when not to use it. So if the image is blurry, you know that you shouldn't use the system. Right? The second benefit is, as a system designer, if you have an explicit characterization of the failure modes, if you can recognize these patterns in the failures, you might be able to design a solution that is specifically catered for that scenario. And the third thing is, using such a characterization, the machine itself might be able to predict when it's about to fail. And so in our upcoming paper at ECCV next week, we show that by using an attributes-based characterization of the failures, the machine can predict its failures more accurately than several strong baselines. For example, if you just use the confidence of the classifier to predict whether the system is going to fail or not, that doesn't work as well as using attributes to characterize the failure modes. All right, so the third scenario that I want to talk about is where you have the human communicating with the machine as a supervisor, right? And one natural thing to communicate is sort of your domain knowledge or your visual common sense about the world to the machine. So for example, we've used attributes to allow a human to say things like polar bears are white and larger than rabbits. And we've shown how you can just take these textual descriptions in terms of attributes and convert them to a visual model that the system can then use to go ahead and recognize polar bears, even though it's never seen polar bears before. And the flip side of this, again, you have a human as a supervisor, but the machine is the one communicating. And we're trying to explore ways in which you can make your machine more interpretable. So you can get your machine to explain why it's making the decisions that it's making. For example, it might say that I think this is a polar bear because I see something that's white and furry. And the nice thing about these last two scenarios is they can give you a way of going back and forth. They give you ways of doing interesting active and interactive learning settings where now that you know what the machine believes, because it's characterizing its decision process, the supervisor might be able to convey certain domain knowledge or visual common sense to specifically clear certain errors that you might see in the machine's current belief. So you might realize that it's learned some weird correlations. That might be because the training data had certain biases, and so you might be able to go back and fix that, give it a better training set to hopefully get more accurate models. Right, so what I'm going to do now is give you one example of this active interactive learning setting that we've explored. So if you look at traditional active learning, right, the way that works is the machine is going to pick an image that it's currently most confused about, and it might ask the supervisor, is this a forest image or not? Right, and the only thing that the supervisor would say is, no, this is not a forest. Right, so this is the traditional active learning setting where the machine is the machine is not expressing its current belief about the visual world. It's just asking the user a question. And the user is only giving you binary labels in terms of, yes, this is a forest, or no, it's not. So what we proposed instead was, one, instead of just asking the question, the machine conveys its belief. In this way, in this case, it's conveying the belief in a very simple way. It's just telling the user what its predicted label for the image is. So the machine is saying, I think this is a forest. What do you think? Right? And the machine and the human, instead of just giving a yes or no answer about whether it's a forest or not, if the machine is wrong, the user provides an explanation as to why the machine is wrong. So in this case, the supervisor is saying, no, this is not a forest because it's too open to be a forest. And what this lets us do is the following. If the machine now has a pre-trained attribute classifier for openness, it can go to a large data set of unlabeled images, identify all the images that are even more open than this query image, and realize that if this image is too open to be a forest, then all these other images that I have that are even more open must not be forests either. Right? It can add those as negative examples for training its classifier and update its model. Right? And so in this way, feedback given to just one image, we showed that you can propagate that to many more images in an unlabeled set and learn the model much faster than you would if you were only getting label-based feedback. Right? Now, one natural question here is, well, in order to identify all these images that are even more open, the machine needs to have a classifier for what open means. Right? And so what we explored after that was, well, what if you don't have these pre-trained attribute classifiers? What if you try and learn these attribute classifiers on the fly? And the question is, can you do that? Right? And the answer is yes, because if you think about it, when the feedback says, no, this is too open to be a forest, yes, that's giving you information about what forests look like, but it is also giving you information about what open means. Right? So if this image is too open to be a forest, and if the machine already has a few example images that are labeled as forests, then those must be less open than this query image. Right? So it can use the same feedback as annotation for updating its attribute classifiers. Right? And so here's one example result that we have. On the x-axis is the number of iterations, is the amount of feedback that you're getting from the user. And on the y-axis is the classification accuracy of the classifiers that you're training to recognize categories. Right? And this is the baseline approach. This is the standard active learning approach that doesn't use any attribute-based feedback. This is what you get if you add in the attribute-based feedback at every iteration. Right? So you see that there's a significant improvement by specifying why the classifier is making certain mistakes. So in other words, instead of just giving label-based feedback, you're also giving attribute-based explanations. And this final curve is what you get if there are two things that change here. One is you learn the attribute classifiers on the fly. And the second is when you pick an image actively, you don't just try to pick an image that is informative in terms of the label-based feedback, but you also try and pick an image that will be informative in terms of the attribute-based feedback. So you also change your active learning model to pick the next image. Yes?
So does this actually say that you're actually learning any faster in terms of the amount of information you're providing the system, because each iteration of the higher ones, you're asking the human to give you much more information than you are in the lower lines.
Right, so we also have another version of the plot where on the x-axis it's the amount of time that the user is spending, and what we find is even if you scale that out by the extra factor, you still get these gains. But I agree that is a more accurate representation. Any other questions? Yes?
In the attribute-based feedback, are you restricting the domain, the language domain, or the kind of...
So in the way the interface is currently set up, yes, there is a list of attributes that the user picks from, but conceptually, especially when you think about the case where you can learn these attributes on the fly, there's nothing that restricts the interface from being more free-form, where the user can type in any word that they want to use. And ideally, what you would want to do in that setting is, so right now, because we have a fixed list, they're always going to pick one of those options. When you move to the free-form situation, you wouldn't expect the user to remember what word they used for a certain attribute in some previous iteration and then use the same word again. And so you might want to append sort of a language model that reasons about the similarities in terms of the meanings of these words being used. But in this particular experiment, it was just a list that they picked from. It was a predetermined vocabulary. They still had the luxury to introduce a new attribute for which no model existed, but they could only pick from a fixed list. Yes?
Sorry, just to actually Ian's question, so how many attributes are there?
So we have several different data sets. I think this is the shoes data set that had about 10 attributes. We also have the outdoor scenes that had about, I think it was 6 to 8 attributes.
So they're providing like 4 bits of information per iteration.
Right, so what we don't have a plot where where the x-axis has the number of bits, and that gets a little bit trickier because these are relative attributes.
Sure.
So you're saying that you're not actually saying yes or no. So I see. But what we've converted this to the time, and I think that is what is perhaps what really matters, that how much more time does the user have to spend to train the system to get the same accuracy. And so when we scale it by that factor, you still see improvements, but we haven't checked.
Right? Because did you use keyboard or mouse for the no attributes feedback?
It was always, so this was on Mechanical Turk, and people are just clicking on radio buttons to give you, using a mouse.
Right, so that's going to be much slower than minus plus.
Right. But I mean, they would have a list of attributes that they would need to still, so unless you have more sophisticated sort of shortcuts to pick one of those attributes and so on. And if it is much slower, that would only make it harder for us to.
No, I'm saying the green curve.
You're saying the green curve would be much faster. I see. Yeah, we haven't reasoned. This was all on Mechanical Turk, and we haven't reasoned about that. That's a good point. The choice of interface, I'm sure, would change the amount of time they have to spend. Yes.
So here the attribute classifier needs to be more accurate than the actual scene or object classifier, yeah? Because if you have a mistake in the attribute prediction, like about things to be too open, then you basically screw up all the recognition, yeah?
So the attribute classifiers don't necessarily need to be more accurate, and in fact, the strange thing with this red curve is that when we learned the attributes on the fly, we actually saw an improvement in performance in terms of the classification of categories, which was a little bit strange to me, because if you have your pre-trained vocabulary, that has used much more supervision to train the attribute ranking functions. And so I expected that when you try and learn them on the fly, you would see a decrease in performance, but that didn't happen. And what we found was the attribute models that you end up learning on the fly are actually worse attribute predictors than what you learn offline, in the sense of them generalizing to previously unseen categories, which is sort of one of the points of attributes. But they end up being catered towards these specific categories to learn these specific concepts. So they're worse predictors in general, but they end up doing a better job at training the category model that you're trying to train in this process. And that's why you see an improvement in performance, which was a bit counterintuitive. Yeah.
So what you're saying is that the attribute model is overfitting to the particular images?
To the particular categories, not the particular images, but the particular concepts that you're trying to learn. So if you're trying to teach it forests, it ends up learning a notion of openness that is relevant for forests, as opposed to learning a general notion of openness that will generalize to other categories.
How do you deal with synonyms? So
Right, so that's what I was saying, that right now we just have a predetermined list, so there are no two attributes that mean the same thing that are on the list. But ideally, when you have a free-form interface where you can just type anything in, you would want to reason about meaning. You would want to have a language model that tells you how similar two words are and share the annotations appropriately so that you're updating sort of all attribute models on the fly, not just the one that the user picked. But our interface didn't allow for that right now. Yes?
So if I understand correctly, the work that you're presenting here, there's two elements to it. One is that the computer is getting attribute information on some images, like saying that this was incorrect, for example, because it's not open enough, and so on. And then there's the other aspect, which is that the human is guiding the computer through the learning process. So the fact that every time it makes a prediction, it gets some feedback on it. Is there a way of reading these plots to separate those two out? So
the green curve that you see here also has a human in the loop that is actively responding to every query that is that the machine brings up, right? So the only difference between the green and the blue is the fact that both of them have a human involved. In both cases, the image is being actively selected. The only difference is that in the blue case, the human is also providing an explanation, right? And that the benefit of that explanation doesn't correspond to just that query image. That doesn't really matter much. The benefit comes from the fact that you can now use that explanation and propagate that feedback to many more unlabeled images. And that's where you get the benefit from. So if you did not propagate that, then the user, the way we have it set up right now, the way I have defined it, the user saying that this is too open to be a forest isn't going to give you any information if you don't take advantage of that and propagate it to many more images to find other negative examples of forests. Does that answer your question?
I think so, yeah.
Okay. Yes.
So here you look at how quickly the classifiers learn. I was wondering if you also ran those to convergence. Can you say something about whether, with the additional information you provide about attributes, you might be able to achieve a higher performance?
So we have an unlabeled data set of images, right? And sort of the point of convergence would be once every single image in that database has been labeled by the user. And at that point, all methods will converge to the same point because they've all been annotated with the ground truth category level labels that the user provides. So if you have enough time to spend, essentially, if you have time to get your entire unlabeled set annotated, then there's no point in using attribute-based feedback. But the idea is that if you only have time to label a few images, you can still take advantage of this unlabeled set in sort of a semi-supervised learning kind of setting by using attribute-based feedback. Yes?
There's a parallel here with early child development. If you teach a child by just saying yes or no binary, it isn't going to learn as quick as you explain to a child why something isn't.
Right. So I missed the first part of the question, but the motivation, like if you read the introduction of this paper, that's exactly the kind of things that we talk about. That if you try and teach a child, you're not going to just say yes or no. You usually explain to the child why something is something or why he or she has misunderstood. But I don't know if you were asking me if we've done studies along those lines or not, and no, we haven't.
There is an obvious parallel.
Right, yes. Exactly, and that is what we talk about, exactly, yeah. Any other questions? Yeah.
So what about subjectivity? Now, I couldn't come up with a category which will require the attribute this is less cool or too cool to be
or this shoe is too formal to wear at a certain event.
So basically, then there's a notion of subjectivity from the human side as well, and then who is your target population? How do you reason about that?
Right, absolutely. And so Adriana Kovashka, one of Kristen Grauman's students, has looked at exactly this, where she looks at attributes that are subjective, and she tries to build models where she personalizes the definition to individuals. And I think she also has some follow-up work where she's not personalizing to individuals, but personalizing to sort of schools of thought, that this entire group of people seem to have the same notion of formal. This other group of people have a similar notion. And she tries to build models that caters to them.
So when you were giving properties for attributes, you said they should be detectable and they should be interpretable. And basically, if you think about subjective attributes, then they are not detectable by definition because there is ambiguity in. Suppose there is a target user. What he or she sort of considers this, whether cool or less cool. And the other thing is about interpretable. Again, okay, you have a notion of, yes, I can associate what that particular attribute would mean, but I don't have a very clear understanding of, it's a very rough concept.
Right. And so we've been talking about this a little bit, where you can sort of, there are these subjective attributes and there are objective attributes. Things like the height of a heel, if you still talk about shoes, and the height of a heel is something that everyone agrees on. And so we're looking at ways in which a user can define his or her notion of a subjective attribute in terms of these objective attributes. And that one can help the machine, so the machine knows what you mean by this, and it's a sort of a similar thing of propagating that information to build your attribute model. And the other benefit is you can also use that to guide a crowd to annotate images for you in a personalized fashion, right? So far there's been this situation where you either go to the crowd and then you lose all personalization if you're getting things annotated, or you have to have user-specific models and then you can't have enough annotated data. And so by having one user describe to the crowd what he means by a subjective attribute in terms of objective, you can guide a whole crowd in a personalized way. So that's something that we're looking at right now. Any other questions? All right. Okay. And you can also use similar ideas for guiding semi-supervised clustering algorithms to a desired clustering by explaining why certain images should belong to the same cluster or different cluster in terms of attributes. So that's also next week at ECCV. All right, so one last element that I want to talk about in this sort of attribute-based human-machine communication is this idea of trying to read between the lines. So in a lot of these situations, I'm telling you that the human provides feedback to the machine, and everything I've said so far sort of takes that feedback at face value. Somebody says, I want a shoe that is more formal, and that's exactly what you do. You go look for shoes that are more formal and return them. But what I'm claiming is that in a lot of these situations, there are opportunities to read between the lines of what the human is saying and actually extract more information from the human without the human having to do any more work. And so I'm going to give you 3 examples of what I mean by this. And again, there won't be too many details in that, but hopefully the ideas will be clear. So the first example is the following. Let's say this is the pair of shoes that you're looking for. You query black shoes. You might get images that look something like this. None of these are quite what you had in mind. And so what I described earlier is you might click on a shoe and say, I want something that's shinier, or click on another shoe and say, I want something that's more formal. And you hope that you would get results that look like this, right? The shoe that you wanted is in one of the top K results. So now clearly from this feedback, yes, you want something that's more formal. Yes, you want something that's shinier. But I'm claiming that the fact that you chose to comment on these particular images and the fact that you chose to comment on these particular attributes in itself conveys some information beyond what's being stated. All right, and let me give you an example to hopefully convince you. Let's say you're looking for a picture of this person. And let's say your top K results so far look like this. Right? Now, what are the chances that you would click on this image and say the person that I was looking for is more feminine looking than this person? Right? That's just not what you're going to do. You're probably going to click on one of these and say that maybe the person I want is older than her, younger than her, or something like that. Right? You will probably click on an image that is somewhat relevant to what you're looking for and then explain how it's different rather than click on an image that's just completely off. Right? And so what we showed is if you take advantage of this, if you take advantage of what I just described here, reason about which reference images the user commented on and which attributes they commented on, in addition to incorporating the feedback at face value, you can do a better job at image search without, again, the user having to do any more work. Right? The user is still giving you the same feedback. Right? So this is one example. Here's another example. Let's say you had to describe these images in terms of these people smiling. Right? Now, it's very unlikely that you will say this person is smiling more than this person. Right? Now, if you had a smiling ranking function, a relative attribute predictor for smiling, and you ran it on this image, that is probably what it would say. It would say that this person is smiling more than this person because she seems to be frowning less. Right? But that's just not how you and I would describe it. We would just say that this seems to be a picture of 2 kids that are not smiling. Right? But for another image that looks like this, we would be much more comfortable saying that these 2 kids are smiling more than this kid in the middle. Right? So certain attributes we naturally describe with certain images we naturally describe with binary attributes, and certain images we naturally describe with relative attributes. And what we try to do is by looking at these images, try and predict which description is more natural. right? And with that, with a model like that, you can do a better job at image search, at textual descriptions of images, and so on, right? So this is another example of trying to read between the lines. If somebody says, find me an image where one person is smiling more than the other person, you should not be returning this image, even though your relative attribute would agree that this is an image where one person is smiling more than the other, right? And here's one last example. If you were looking for an image that looks like this, what would you query for? You might say, I'm looking for white furry dogs, right? And now how happy would you be if you got this result back? Right? Now, this is a completely valid white furry dog, but that's just not what stands out. That's not what's dominant about this image, right? If you wanted an image like this, you would have said something like, find me a scary looking dog, or a dog that's barking viciously, or a dog that has sharp teeth, right? You would not describe this as a dog that's white and furry. And so if your query is white furry, I should not be returning images like these, because the whiteness and furriness is not dominant here, it's dominant here. And so these images should have a higher relevance or a higher rank. And again, we can model this, and we showed that you can do better at image search, textual descriptions, and so on. All right, so overall, for this part of my talk, I've talked about how we've used attributes to access a user's mental model when they're trying to do something like image search. I've talked about how we've tried to use attributes to make our computer vision systems more usable while they're still imperfect by getting them to characterize their failure modes. I've talked about how we're trying to use attributes to make our machines more interpretable, where they're explaining why they're making the decisions that they're making and not just spitting a decision out. And trying to use attributes to teach machines sort of visual common sense or domain knowledge that we all have and convey that to machines. And in these two elements, I talked about how you can try and make the human's job easier, where you elevate some of the effort while still getting the same information out. Right? So all in all, trying to use attributes to enhance human-machine communication with the hope of doing a better job at visual recognition. All right, so in the next part of my talk, I want to talk about something somewhat related but a little different. So I mentioned that one of the uses of attributes is for humans to convey sort of visual common sense to machines, right? And so far I've talked about a very direct communication where you explicitly just say that zebras are striped and they have 4 legs. Right? But the question is, can we learn this? Can the machine learn this knowledge automatically just by observing the visual world around us? Right? And so if you look at an image like this, and if you had to describe it, you might say that this is a picture of 2 professors conversing in front of a blackboard. Right? And now some of you might have seen this example, but if you had to explain why you think this is a picture of 2 professors, right? We might say that, well, these are probably professors because they look fairly distinguished. They have receding hairlines. They're standing in front of a blackboard. Why do we know it's a blackboard? Because there's sort of complicated equations written all over it, and so on. Right? Why do we think they're conversing with each other? Because they're looking at each other. Right? And if I change just one subtle thing about it, right? If I show you this image instead, our description would change. Right? We would no longer believe that they're talking to each other. We would think that these are 2 professors standing in front of a blackboard, right? And now the key is, how do we get machines to learn this? How do we get machines to realize that just one difference, one sort of visual feature in terms of gaze, when that changes, it changes the entire meaning of the scene, right? And so there's a few challenges in trying to be able to do this, just have machines learn this, right? One issue is the lack of visual density. We don't have access to such pairs of images where the only thing that's changing is one subtle feature, for example, the gaze of 2 people, right? We just don't have that. We don't have access to such data sets. So it's hard to learn how just the change in a gaze changes the meaning of the scene, right? That's one problem. The second problem is, even if we somehow had this visual density, we would have to go ahead and annotate every single thing about the image: receding hairlines, distinguished looks, suits, ties, gaze, expression, blackboards, equations on blackboards, everything. Right? And annotating that is expensive and quite boring, right? So it's going to be hard to get people to do that. And so then we all wish that, well, maybe we can just automatically detect all this, right? We're in the business of doing computer vision. We can just have it detect everything. But we're nowhere close to that. We don't have accurate algorithms that can accurately detect receding hairlines and distinguished looks and so on. So we sort of have this chicken and egg problem, right? We want to learn this common sense so that we can do a better job at visual recognition. And we're saying that in order to learn this common sense, we need to solve visual recognition so that we can extract all these attributes and objects from images to actually learn the common sense. Right? And so what we're claiming is to break out of this sort of vicious cycle, we should just maybe give up on photorealism. Right? I'm asking if to learn common sense, to learn the essence of the visual world, do we really need access to real images, or is there something else that we can learn this from? Right? And so what we proposed was to try and learn this common sense from an abstraction of our world. So a world that is still visual, still conveys the same essence of the visual world around us, but is not photorealistic. All right? And so we introduced these two characters, Mike and Jenny, and we created this world of different toys and background objects, different animals, fun hats and food items and so on that they could use. And Mike and Jenny can have different expressions and different poses. And what we built was this extremely straightforward interface that allows people to sort of drag and drop objects onto the scene, change the depth by changing the size, flip objects around, choose different expressions, different poses, and you can create this little scene fairly quickly that's very simple but does have quite a bit of meaning in it, right? If I asked you to write a few sentences describing this, you would be able to do a reasonable job, right? And so now once we have this interface, we can do fun things with it. One thing we can do is we can show people a sentence. For example, here's a description. Mike fights off a bear by giving him a hot dog while Jenny runs away. And you can tell these are fun things to work on, right? But so we can give this description to 10 different people on Mechanical Turk, and we can have them all create a depiction of this sentence using our clip art, using our interface. And the nice thing is they're all going to create different scenes, right? The objects are different, their locations are different. Some of them have trees, some of them don't. They have different kinds of trees. But the common thing is they all have Mike, Jenny, the bear. Mike is always facing the bear with the hot dog in his hand, and Jenny is always running off in the opposite direction. Right? So now with this gives us access to a set of images that are very different, but they all have the exact same meaning. And we can now start analyzing what is it that's common amongst these images and realize that those features must be the ones that are relevant to the meaning of the scene. Right? And this is something that is almost impossible to get with real images. You can never find multiple images with the exact same meaning. Right? And so we created this data set of 1,000 sort of semantically similar classes. So we have these 1,000 descriptions, and each one has a group of 10 images corresponding to that. And you can do a lot of interesting things. And so the nice thing about this data set is it's completely annotated, right? You have a pixel level segmentation. I mean, by definition, this is an abstract world. This is made from clip art. So every single pixel has a semantic category labeled. You have all the attributes labeled. You have the gaze labeled. You have the poses labeled, everything, right? All the parameters of this abstract visual world, you have direct access to, right? And now we can start thinking that, okay, if you have object detection, attribute detection, pose detection solved, now can we actually do a reasonable job at understanding the meaning of the scene? And that is still an open problem. It's not trivial to go from these annotations to, for example, a description of the scene that would convey the meaning and not all the irrelevant details. Right? And so now we can finally start studying those problems without having to wait for object detection and attribute detection to be solved. Right? So we did a few things with this. One thing is we tried, as I said, we tried to reason about which visual features are important to the meaning of the scene. And we can also start building an explicit mapping between visual features, for example, relative location or gaze or expression, and textual phrases. So we can learn that running away means the person is facing the opposite direction from whatever subject he or she is running away from and is in a running pose. Right? So we can learn that explicit mapping from this data set. And so with that mapping, we can do something like this. We can take an input description that says Jenny is catching the ball, Mike is kicking the ball, the table is next to the tree. And we can do some straightforward natural language processing to extract tuples from this description. Jenny catch ball, Mike kick ball, table B. And you can see that there's an error here. We're missing the tree, and we haven't quite figured that out. But now from these tuples, using the mapping that I just described in the previous slide, we can automatically generate an abstract scene that corresponds to this input description. Right? So the machine has automatically sort of imagined a scene that corresponds to this fairly brief story that you see up there. And it makes a lot of sense. Mike is kicking the ball, Jenny is catching the ball, and the tree is missing because the NLP processing missed that. Right? And just for reference, this was the ground truth scene that corresponded to it. So the ball is different, Mike and Jenny are at different locations, but the meaning has been maintained. Right? And so then what we wanted to do was try and use this for something much more specific. Right now I'm talking about genetic scenes and genetic descriptions. And what we tried to do here is have people create illustrations of very specific interactions between people, 60 different fine-grained interactions like dancing with, holding hands with, running away from. And here they're creating a scene that person A is dancing with person B. It looked like the person is actually maybe hitting the other person, but as soon as they change the expression, the entire meaning changes. Right? And so people can illustrate whatever they believe is a good illustration of these 60 different fine-grained interactions. And these are some examples of what Mechanical Turk workers created for jumping over, holding hands with, dancing with. And if you look at the dancing with, it's a nice diverse collection of different depictions, different canonical poses of what dancing with might look like. And so then what we do is we use just these visual abstractions, just this clip art, to train a model for what these interactions mean. And then we downloaded images from the web that depicted each one of these 60 different phrases. And we tried to use those models trained only on visual abstractions and use them to detect these interactions in real images. Right? So this is sort of an extreme domain adaptation task, if you will. Right? And you can also think of this as zero-shot learning. Right? Our models haven't seen any real examples. This is just people depicting their understanding of these phrases. Right? And so this is a snapshot of what the results look like. So this would be your accuracy by chance because you have 60 categories. And this is what you get when you train on these clip art and use it on real images. Which is, I mean, the actual accuracy is not all that high, but it's fairly impressive for zero-shot learning, that you've never seen what a person dancing with another person looks like in real images, but you can still detect it. Right? And so here what we're using is the ground truth pose on the real images. We're not interested in solving the pose detection problem. What we wanted to see was if you have good pose detection, does the meaning of what it means to dance, for one person to dance with another person, does that carry over to real images? Right? Does the common sense learned from abstract images carry over to real images? But for completeness, and given that I'm in computer vision, we actually ran the pose detectors, and this is what you get with real pose detection on real images. All right, so all in all, we've been trying to use visual abstraction for studying mappings between images and text or images and meaning. I showed you how we've tried to use visual abstraction for zero-shot learning to train models for specific concepts that you then want to detect in real images. We're also trying to use visual abstraction to study things like image memorability. So for real images, people have shown that certain images are much more memorable to human subjects than other real images. We found the same thing to be true for these clip art scenes, and we're trying to understand what is it about these scenes that make them more memorable than others. We're also looking at specificity. So if I show 10 different people one clip art scene, and I ask them to write a description, for certain scenes, these descriptions are extremely consistent. They talk about more or less the same thing. But for other scenes, these descriptions vary quite a bit. And so we're trying to understand what kinds of scenes are so specific that everyone thinks of the same thing when they look at it, but why are some other scenes less specific that people write different descriptions? And as I mentioned, we're also trying to see if we can learn common sense from these abstract images and apply them to improve visual recognition on real images. And the high-level point being that this is exciting because we can start studying these problems without having to deal with all the errors that we get with object detectors, attribute detectors, pose detectors, and so on. And of course, this goes beyond Mike and Jenny. So we're in the process of collecting a data set that is much larger, has significantly more realistic clip art. It's people of different ages and different ethnicities, many more poses of the animals, indoor scenes, outdoor scenes, and so on. All right, so with that, I'll conclude. I started by talking about this gap in the performance of humans and machines as far as several semantic image understanding tasks go. And I argued that if we have a better way for humans and machines to communicate, maybe we can make some progress in terms of bridging this gap. I talked about human-machine communication for two goals. One is to let humans convey their domain knowledge or their common sense to machines. And the second is to make our machines more interpretable for humans so that we understand them better and we can make these systems more usable. I talked about two different modes of communication. One was sort of a very direct mode of communication in terms of attributes or text. And the second is much more indirect. It's based on illustration, and it's based on sort of abstracting the visual world down to the semantic entities that we care about, and then see if we can study these high-level tasks. And so all in all, tying back to the title of my talk, trying to use humans for more than just sort of these binary labels on images. Thank you.
So we have time for questions.
In your image search examples, what do you visualize the application as being? Is it clip art or personal photos?
For the image search using attributes?
Using anything.
So for the attributes, we had a variety of applications in mind. One was sort of online shopping, that when you're trying to buy shoes, it's very convenient to click on an image and say that I want something like this, but with higher heels, or something that's a darker color, or a brighter color, or is a shinier shoe. It also makes a lot of sense for sort of law enforcement type applications where someone may have witnessed a crime, they saw the person, didn't get a chance to take a picture, they show up at a law enforcement office, and there's a database of pictures that you're trying to find that one person from. So you can click on an image and say the person I saw had longer hair or lighter skin or was fuller faced and things like that. Even like a lot of times when I'm making talks, I have a particular image in mind that I'm trying to look for. So all those scenarios where you have a fairly accurate picture of what you're looking for, you just don't have the actual picture, which is why you're trying to search for it. And so there, I think a lot of times users, it's very natural to describe it in terms of attributes relative to other things that you see. If I were to just describe it in free form, that might be hard. But when I see something, it's easy for me to say how what I want is different.
I was very impressed that your system could generalize from those clip art images to real photos. And I was wondering if you can say something about what kinds of features that you might have picked up.
Right. So we cannot be using any features that are appearance-based, right? So we can't extract any texture, color, etc. So the features that we extracted were things like the pose, so the joint angles, the expression, the gender. We also looked at the location of one person's joints with respect to the other person's sort of torso, head, and things like that. So all those the things that you can extract once pose detection is already solved. So those are the kinds of features that we extracted from there. Sure.
Okay, if there are no more questions, let's thank Devi again.
Thank you.